Hello everyone and welcome to the lecture on the basic optics and microscopy. My name is Lisha Patil and today we'll explore how light behaves both as a fundamental wave and as a powerful tool for scientific visualization. So, optics and microscopy form the absolute backbone of analytical science, allowing us to investigate everything from microscopic materials to complex physical evidence. Over the course of this presentation, we'll bridge the gap between pure optical physics, such as wave interference and interferometry, and the practical high-precision microscopic configurations used in modern research laboratories. Now, to give you an overview of today's session, our discussion is divided into two primary segments. First, we will establish the foundational physics of basic optics. We will look at light as an electromagnetic wave, discuss the crucial principle of superposition, examine spatial and temporal interference, dive into Thomas Young's historic double-slit experiment, and conclude the physics portion with the Michelson interferometer and its real-world application. Now, in the second half, we'll transition into microscopy. Here we will dissect the mechanics of how a microscope actually forms an image, define critical parameters like numerical aperture and resolving power, and finally look at specialized microscopic setups ranging from standard compound and comparison systems to advanced fluorescence and electron microscope. Now let's get into it. We'll start with our first part, that is basic optics. Now let us begin with the basic optics by defining what light actually is. So, light propagates through the vacuum of space as a transverse electromagnetic wave. When we say transverse, it means that the oscillations occur perpendicular to the directions of the wave's travel. Specifically, light consists of two mutual perpendicular time-varying factors. As an electric field E and a magnetic field B, these oscillating fields continuously regenerates one another, allowing the wave to self-propagate through space completely independent of any physical material medium. This behavior perfectly satisfies James Clerk Maxwell's foundational wave equation. Mathematically, the speed of light in a vacuum denotes as c. Now, it is a fundamental constant tied directly to the intrinsic electrical and magnetic properties of free space. It is defined by the formula where epsilon naught is the vacuum permittivity and nu naught is a vacuum permittivity. However, when light leaves a vacuum and travels within a physical material such as glass, water, or a polymer, its velocity drops dramatically. Now, this reduction depends on the material's relative permittivity, that is epsilon r, and relative permittivity, that is nu r. This interaction dictates the material's structural refractive index, that is N, which we calculate using the classical ratio of the speed of light in a vacuum to the velocity in the medium, that is N is equals to C upon V. Now, the principle of superposition. Now that we understand how an isolated light wave propagates, we must ask what happens when multiple waves cross our paths. The answer lies in the principle of superposition, which is the fundamental law governing how overlapping wavefronts interact within the same physical space. The principle states that when two or more waves travel through a medium and intersect at an exact coordinate, the net displacement of the medium at that point is simply the vector sum of the individual displacements caused by each independent wave. If we represent two overlapping wave functions mathematically as y1 xnt and y2 xnt, the result combined the wave profile, that is yxt, is modeled as a simpler linear combination. Crucially, because this principle operates linearly, the intersecting wave passes through one another completely unaltered. They do not bounce off each other, scramble, or lose their energy. Instead, they retain their original trajectories, frequencies, and amplitudes after moving past the region of intersection. This linearity is what allows complex optical interference and imaging to occur without destroying the underlying information carried by the light. Now, the interference of light. Building directly upon superposition, we arrive at the phenomenon of interference. Interference describes the spatial and temporal redistribution of light intensity that occurs when two or more coherent electromagnetic wavefronts overlap in space. It is important to note that you cannot take any two random flashlights and see an interference pattern. To observe stable, recognizable interference, the interacting light sources must meet two strict conditions of coherence. The first one is temporal coherence and the second is spatial coherence. Now, for the temporal coherence, the overlapping waves must maintain an identical wavelength and frequency, that is lambda. If the frequencies are different, the pattern will change too quickly for the detection. Now, spatial coherence. The waves must maintain a constant, unshifting phase relationship over time. When these conditions are met, we observe two extremes. First, when the phase difference delta phi equals an even multiple of pi, or when the physical path difference, that is delta x, is an integer multiple of the wavelength, that is delta x is equals to m by c dot by lambda. The wave crests align exactly with other crests. The trigger constructive interference, maximizing the local light amplitude and creating a bright zone. Conversely, when the phase difference is an odd multiple of pi or the path difference is a half integer multiple of delta x is equals to m plus 0.5 by c dot by lambda. The crests align directly with the troughs. This causes destructive interference, completely cancelling out the wave amplitudes and producing an absolute minimum of light intensity, resulting in the darkness. So, our next topic is two-slit interference, that is Young's experiment. To prove this wave nature of light, Thomas Young performed his historical double-slit experiment in 1801. In this setup, unpolarized monochromatic light passes through a pair of narrow parallel slits separated by a small physical distance, that is d. This acts as an elegant way to split the incoming light into two highly synchronous, coherent secondary sources. These sources spread outward as spherical waves and project onto a distant viewing screen located at a distance, that is capital D. As these two paths overlap, they form alternating light and dark bands on the screen, known as interference fringes. The exact positions of these fringes are entirely determined by the path difference, that is delta x is equals to d upon c dot upon sine theta, between the rays traveling from each slit to any given point on the screen. On this slide, you can see the structural formula used to define these fringes' position. For the bright fringes, that is constructive, and for the dark fringes, that is destructive. When m represents the fringe order integer, that is m can be 0 or +1 or +2 and so on. This elegant experiment provides irrefutable proof that light behaves as a wave, as particles would not behave this way when passing through two slits. See, this is the two-slit interference, that is fringe width. Let's take Young's experiment a step further into mathematically, practically now, because the distance is on the screen, d is typically much larger than the slit separation, that is small d. The angle theta is incredibly small. And under these conditions, we can confidently apply the small angle approximation where sin theta is proportional to tan theta, that is y upon d, with y being the linear distance from the central maximum on the screen. By substituting this approximation into our path difference equation, we can isolate the linear distance between any two adjacent bright bands or two adjacent dark bands. These distance is known as the fringe width, denoted by the Greek letter beta. It is calculated using the formula. Now, the Michelson's interferometer and applications. So, moving on from double slits, let's examine one of the most precise optical instruments ever, the Michelson's interferometer. This device splits an incident beam of coherent light into two independent paths, lens them independently, and then recombines them to produce highly accurate interference fringes. Now, let's look at the optical mechanism, that is monochromatic light hits a semi-reflective beam splitter oriented at a precise 45-degree angle. This splits the light into two identical paths traveling along perpendicular tracks. One beam travels toward a fixed reference mirror designated as M1, while the other travels toward the movable mirror designated as M2. Upon reflecting off their respective mirrors, both beams return to the beam splitter, where they recombine and project an interference pattern into an output detector or viewing piece. Now, pay close attention to the physics here, because the light must travel to the movable mirror and back. If the movable mirror travels physical of linear distance of delta x, the total optical path difference shifts by exactly twice the amount, or 2 upon c dot upon delta x, is cause the fringe patterns to shift across the field of view according to the relationship. This allows us to track physical movements with a precision equal to fraction of a single wavelength of light. Now, because the Michelson's interferometer is incredibly sensitive to changes in the optical path, it has vital primary applications across multiple scientific and industrial domains. The first one is metrology and distance calibration. It allows the measurement of physical displacements down to sub-nanometer scales simply by tracking shifting fringe lines. It is widely used in semiconductor manufacturing and precision engineering. The second one is refractive index determination. If we insert a thin transparent sample or a gas chamber into one of the arm pathways, the light slows down in the arm by tracking the resulting shift in the interference pattern. Researchers can calculate the material's exact refractive index with the high precision. And the last one is the Fourier transform infrared spectroscopy. We can call it FTIR as well. So, this is perhaps one of the most famous analytical rules. The interferometer serves as the core analytical engine in FTIR spectrometers. By capturing the complex interference profile across a range of infrared wavelengths, it allows for the rapid identification of unknown chemical mixtures, explosive residues, and polymer coatings, making it an indispensable tool in material science and forensic analysis. Now, we'll move into our next part, that is advanced microscopy. So, to truly appreciate modern microscopy, we must first understand the multi-stage optical process that governs how an image is actually formed. Image formation relies on a beautiful combination of light refraction, sample diffraction, and geometric focus. First, light from an illumination source passes through a condenser lens system. The sole purpose of the condenser is to focus a tight, even cone of illumination directly onto the specimen. As the intense light encounters the sample's microscopic structure, it breaks into a complex series of diffracted wavefronts. Next, the objective lens system captures these scattered, diffracted rays. It focuses them to form a magnified, inverted, real intermediate image within the body tube of the microscope. Finally, this intermediate image acts as the object for the ocular or eyepiece lens. The ocular magnifies the intermediate image a second time, projecting a final, highly enlarged virtual image directly onto the user's retina or a digital camera sensor. It is uh, it is this two-step magnification process that defines the compound optical system. Now, the numerical aperture and resolving power. So, when evaluating a microscope, a common misconception is that the total magnification is the most important factor. In reality, the microscope's ultimate performance is determined by its resolving power. Its structural ability to distinguish fine details and separate two closely spaced features as distinct individual entities. Magnification without resolution is just empty magnification. It only gives you a larger, blurry image. Now, the primary driver of resolving power is numerical aperture, that is NA. NA is a dimensionless metric that quantifies the light gathering capacity of an objective lens system. It is governed by the opening half angle of the objective's light collecting cone, that is sigma, and the refractive that is alpha, sorry, and the refractive index n of an medium sitting between the objective's front lens elements and the specimen. The mathematical formula that we can say is Na is equals to n dot sine alpha. Because the refractive index of the air is approximately 1, the maximum theoretical Na of a dry lens can never exceed 1. To maximize the Na value, precision objective lenses are engineered to use fluid immersion method. By placing specialized immersion oils which have the high refractive index of 1.515, that is directly between the lens and the cover slip, we match the refractive index of the glass. This prevents the light loss from total internal affection at the cover slip boundary, funneling more light into the lens and dramatically boosting the resolution. Now, to quantify this resolution limit, we'll look at the D minimum, which represents the minimum physical distance required between 2 points for them to be resolved as separate objects. If two details are closer together than D minimum, they will blur into a single spot. This limit is dictated by wave diffraction and can be calculated by Abbe's resolution limit. So, now where lambda represents the illumination wavelength, alternatively, if we apply Rayleigh's criteria, which is tailored for pinpoint self-luminous objects, so this formula provides the clear direction for optical engineering. If you want to achieve a finer resolution, meaning a smaller D minimum value, you have only two physical choices. You must either shift to shorter wavelengths of light, that is lambda, such as moving from white light to blue light or UV, or you must increase the numerical aperture, that is Na, of your objective lens system. This is the fundamental physical barrier of the optical microscope. So, now that we have established the underlying physics of image formation and resolution, let us look at the specialized microscopes configuration development to highlight specific material structures and in details. We begin with the most fundamental design, that is the simple microscope. The basic optical configuration uses a single convex lens element or a small group of lenses acting closely together as a single unit. To produce a magnified virtual image of an object, the key requirement here is that the object must be positioned within the lens focal length. Handheld jewelers, loupes, linen testers, and simple reading magnifiers are classical example of this configuration. While limited in magnification and prone to optical aberration at high powers, the simple microscope remains highly useful for quick, low magnification field inspections. Now, we have our compound microscope. When we need magnification beyond what a single lens can provide, we step up to the compound microscope. The compound microscope overcomes the limitations of a single lens by utilizing a multi-lens architecture split into two distinct optical stages. First, the objective lens group sits closest to the specimen, capturing the initial diffracted light and forming a real inverted intermediate image. Now, second, the eyepiece or ocular lens group targets the intermediate image, magnifying it a second time for the viewer. Because of this two-stage magnification, the system achieves a much higher total magnification than a simple lens. The calculation is straightforward and multiplicative. For example, if you use a 40x objective lens combined with a 10x ocular lens, your total structural magnification is 400x. This setup forms the foundation of standard biological and materials examination. Now, moving on to our next microscope, we have specialist microscopic configuration. So, next let us consider the stereoscopic microscope, often referred to as a dissecting microscope. Unlike a standard compound microscope, which provides a flat two-dimensional view, the stereoscopic microscope features two completely separate optical pathways. Each pathway is equipped with its own independent objective lens and eyepiece in alignment. By keeping the optical channels separate, the instrument projects two slightly different viewing angles to the user's left and right eyes. This mimics natural human binocular vision, providing a true three-dimensional uninverted image. Because the image is right side up and exhibits depth perception, it is ideal for physical manipulation, such as dissecting biological specimens, sorting microscopic components, for examining the surface details of large, bulky, and opaque structures like tool marks or electronic components. Now, for materials with highly ordered internal structures, we use the polarizing microscope. This system is built upon a standard compound microscope framework but integrates two specialized polarizing filters directly onto its optical pathway. The first filter, called the polarizer, is positioned below the stage and restricts the incoming illumination to a single plane of vibration. The second filter, called the analyzer, is placed above the objective lens and is typically oriented at a 90-degree angle relative to the polarizer. When no sample is present, there's crossed polars block all light, resulting in a dark field of view. However, when you introduce a bifringent and anisotropic sample, such as mineral cross-sections, drug crystals, or synthetic fibers, the material's order structure splits the polarized light into two pathways, traveling at the different speed. When these paths recombine, they reveal beautiful, vibrant interference polars and the cross polars. This allows researchers to identify unknown crystalline materials and fiber types based purely on their optical crystallography properties. Now, for our second specialist microscope, we have our comparison microscope. In fields like forensic science, side-by-side verification is critical. This led to the development of the comparison microscope. This setup consists of two entirely identical compound microscope stands connected by a shared optical bridge and a single viewing eyepiece. The optical bridge takes the light paths from both independent microscopes and combines them, allowing the user to see a split field view of two separate specimens simultaneously. One half of the eyepiece shows the sample on the left stage, while the other half shows the sample on the right stage. This configuration enables direct comparative analysis of fine details, tool marks, or matching patterns. For instance, a forensic examiner can place a question bullet on one stage and the test fired bullet on the other, aligning the microscopic striations across the split line to determine if they were fired from the same weapon or not. Now, moving on to our next microscope, that is fluorescence microscope. So, traditionally, microscopy relies on light reflecting off a transmitting through a specimen. Fluorescence microscopy, however, treats the specimen as the actual light source. The system uses high-intensity, short-wavelength excitation light, typically ultraviolet or deep blue radiation, to illuminate the specimen. When the energetic light encounters natural fluorophores or targeted chemical stains within the sample, it excites their electrons to higher energy levels. As these electrons drop back down to their ground state, they release that energy by emitting a longer wavelength, lower energy visible light. There are specialized filters within the microscope blocks that the harsh excitation light from reaching the user's eyes, allowing only the emitted fluorescence to pass through. This produces a highly sensitive, high contrast image where specific structures glow brightly against a completely dark background, which is useful for tracing cellular proteins, DNA markers, or specific chemical trace evidence. Now, finally, we reach the absolute pinnacle of resolving part, the electron microscopes that are SEM and TEM. As we discussed earlier via Ebb's limit, visible light microscopy is fundamentally bottlenecked by the wavelength of photons. Electron microscopes completely bypass the resolution limit of visible light by replacing the light waves with a highly focused beam of light velocity electrons. Because these accelerated electrons have wavelengths up to 100,000 times shorter than visible photons, they can resolve features that are orders of magnitude smaller. Electron microscopy is divided into two primary configurations. First one is transmission electron microscope, that is TEM. So this system passes a high energy electron beam straight through an ultra thin sample size by detecting the electron that exit the other side. It provides extremely detailed internal structural resolution down to individual atomic scales. And the second one is scanning electron microscope. Instead of passing through the sample, the SEM scans a focused electron beam across the surface of a specimen. It tracks the emitted secondary or backscattered electrons knocked off the surface. This data is reconstructed to generate high-resolution three-dimensional image of the specimen's intricate surface topography, offering the unmatched depth of field. So, that concludes our deep dive into the basic optics and advanced microscopic configuration. We have traced the path of light from a self-propagating electromagnetic wave through the rules of interference and superposition, all the way to the advanced optical engineering that allows us to see individual atoms. Thank you for all your time and attention.